Hi everybody. In this screencast, I'm going to discuss hydrogen bonding. So hydrogen bonding is our last type of intermolecular force, and it's the strongest type of intermolecular force. And it exists as the force between a hydrogen atom and a very electronegative atom on a neighboring molecule. And that very electronegative atom that isn't the hydrogen is always one of three molecules. It's always either F, O, or N. It's always one of those atoms, F, O, or N. Sometimes I'll joke that hydrogen bonding is FON, F, O, and N, because fluorine, oxygen, and nitrogen are the only atoms, the only elements that can hydrogen bond. So one of those elements has to be present in order for the molecule to be hydrogen bond, and it has to be bonded to a hydrogen. So somewhere in the molecule, we have to have a nitrogen bonded to a hydrogen, an oxygen bonded to a hydrogen, or a fluorine bonded to a hydrogen in order for hydrogen bonding to occur. The reason that it's these three elements is because these three elements have very, very high electronegativities. And because they have such high electronegativities, they leave the hydrogen nucleus exposed. They pull on the electrons so hard that they pull them all away from the hydrogen. And so these partial positives and partial negatives for these molecules are much larger than a typical dipole-dipole force because these elements are so electronegative. The actual attraction that occurs is between the exposed positive hydrogen and the lone pair on any one of these three elements. The lone pair on nitrogen, the lone pairs on oxygen, or the lone pairs on fluorine. So how can we draw this? How can we draw a hydrogen bond? So if I want to show two water molecules hydrogen bonding, I will show water molecules as we've drawn them in the past as hydrogens bonded to oxygen. And I'll draw neighboring water molecules, because if I'm showing an intermolecular force, I need at least two molecules. Forgot a lone pair there. And now I said that the hydrogens are partial positive, the oxygen's partial negative. So our hydrogen bond occurs between the lone pair of an oxygen and a neighboring hydrogen. So our hydrogen bond would be right here. This is our hydrogen bond. And it's very strong, again, because oxygen is so electronegative, that this is a very large partial negative, and this is a very large partial positive on the hydrogen. Notice we don't want to confuse our polar covalent bonds, which are here, those are our covalent bonds, with our intermolecular force. Hydrogen bonding is a confusing name because it's not a classical bond. It is an intermolecular force. So it's poorly named. And we don't want to confuse the hydrogen bond with the covalent bond that exists within the molecule. So this is showing what I just drew. Our hydrogens being attracted to our oxygens in a hydrogen bond, which is shown there and shown there. In an actual sample of water, we have so many molecules that the water molecules actually form two hydrogen bonds with neighboring water molecules. Or I should say the oxygen forms two hydrogen bonds with neighboring molecules. So this oxygen right here has formed a hydrogen bond here and a hydrogen bond here. And then each of the hydrogens that are bonded to this oxygen have their own hydrogen bonds to other neighboring water molecules. So a single water molecule can form up to 4 hydrogen bonds, 2 for the lone pairs on the oxygen and 1 for each hydrogen that is in the molecule. Some other molecules that can undergo hydrogen bonding would be something like ammonia or hydrogen fluoride. Okay? So both of these molecules have either an N, an O, or an F bonded to an H. So NH3, this molecule can hydrogen bond, I could put a neighboring ammonia right here, and we could get a hydrogen bond between these two molecules, right? Just like that. Positively charged hydrogen attracted to a lone pair on the nitrogen. And this is showing an ammonia molecule hydrogen bonding. Again, it's between the negatively charged lone pair on the nitrogen and the positively charged hydrogen. Methanol is another molecule, CH3OH, that can hydrogen bond. If we were to draw methanol, we would see that we have an OH group sticking off. And because we have an OH group, we can form hydrogen bonds. So neighboring methanol molecules can form hydrogen bonds between this lone pair on the oxygen and an adjacent hydrogen. All right, so there's the rest of our methanol molecule would be over there. And that's what's shown up here, methanol hydrogen bonding. Hydrogen bonding is extremely important in biology. Hydrogen bonding is what holds together DNA. You may recall this from last year, but it shows up all over the place in biology. It shows up in the structures of proteins and in all sorts of biological molecules. Because hydrogen bonding is so strong, molecules that can hydrogen bond tend to have a very, very, very high boiling point relative to other molecules because it's our strongest IMF. And a good example of this is comparing butanol to pentane, because butanol and pentane are pretty similar molecules. They have roughly the same mass and roughly the same shape. However, because butanol can hydrogen bond, it's got this oxygen bonded to a hydrogen, which is going to be partial positive. Then neighboring butanol molecules have strong forces of attraction between them. And that leads to a high boiling point for butanol compared to pentane. Notice we have a difference of almost 100 degrees here, even though their mass is the same and their structure looks similar. But this oxygen bonded to this hydrogen makes a big difference in their properties. Here's another question where we have to apply our knowledge of hydrogen bonding. Given that they have the same shape, bent, which of the following molecules would have the highest boiling point? So oxygen, sulfur, selenium, and tellurium are all in the same group on the periodic table. So they all form bent molecules when they bond with hydrogen. But only one of these molecules can hydrogen bond, and that's water. The rest of these cannot hydrogen bond because they don't contain oxygen, nitrogen, or fluorine. So water is going to have the highest boiling point. And we can see that on this graph on the right here, on the left, excuse me, graph A. Notice that water's boiling point is substantially higher than the rest of these molecules. Also notice that for the other three molecules, the boiling point does increase as we go down the group. So the larger molecules, the boiling point goes up. You should be able to explain why we also see this trend of increasing boiling point for these three elements, these three molecules, using your knowledge of our other intermolecular forces. Now that we've covered all three types of intermolecular forces, we want to be able to compare them to the other two types of bonds that we've learned about this year. So intermolecular forces are really, really weak compared to ionic and covalent bonds. Okay? We've learned about dipole-dipole and dispersion forces. Those are our weakest intermolecular forces. Notice how little energy it takes to break them. Hydrogen bonding, it takes more energy to break those, but not nearly as much energy as it takes to break ionic and covalent bonds. So intermolecular forces are all weaker than ionic and covalent bonds. Okay, everybody, that's it for this screencast. I hope this was helpful.